Hello, everyone. I hope you guys are all having a good week. We are covering 12.3 geometric sequences. All right, let's go ahead and get started. 12.3. So last time we covered arithmetic sequences. So here we are doing geometric. We will also look at the sums of geometric sequences. So some formulas are going to be introduced here. All right, before we get into the formal nth term of a geometric sequence, let's start off with a simple definition and some examples, and then the formula. Okay, so definition here. Okay, so the sequence A1, A2, A3 is a geometric sequence if you take any of the terms, any term in the sequence, and divide it by the one before it. So if you take any term in the sequence, divide by the one before it, it equals some constant r, okay? Where r is the constant ratio. Okay, so last time with the arithmetic sequence, we had a common difference where you took any term in the sequence and you subtracted the one before it, and you got the same constant. So here for geometric, you're not subtracting, but you are dividing by the one before it, and you should always get the same number. Okay, so let's take a look at some of these. Let's take a look at these two examples and see if you can tell which one is the geometric sequence. So determine if the following are geometric sequences. Okay, so let's take a look at this first example, 2, 6, 18, 54. Okay, so let's take a look at this sequence, and we will take a look at this one as well, 3, 23, 43, 63. Okay, so we want to do some sort of organized check here. So I will start with the 6, divide by 2, I get 3. 18 divided by 6, I get 3. And 54 divided by 18, I get 3. Okay, so this one here is a yes. And our common ratio would be 3. Okay, this one over here, 23 over 3, whatever that turns out to be, 7 2/3. Okay, 43 divided by 23, and that's not the same. That's not going to be, well, whatever that is, it's not 7 2/3, right? So we can stop right there, and this would be a no. Okay, that one is actually arithmetic. We see that we keep adding 20 to get the next term. Okay, so the nth term, or the function for the geometric sequence. So for the test, definitely have, you can use a sheet of formulas. So that's what I would normally do, even if we were meeting face to face for this chapter here, chapter 12. Okay. So here we have AN equals A times R to the N minus 1. Okay. And here, let me say a few things about this. Okay, so the A here is actually the same as A1, okay, which is your first term. And what happens when you work these all out is you get your sequence that looks like this: A, and then A times R, and then A times R squared, A times R cubed. So you keep multiplying by R to get the next term. Okay, so hopefully you notice that. And we're going to be using this here to find specific terms when we're not given the first term. Okay, kind of like with the arithmetic. Okay, and R is the common ratio. Okay. All right, so let's take a look at this example here. Find A1, R, and AN for the geometric sequence. So suppose I have this sequence: -3, -6, -12, -24. Okay, so clearly this is geometric, because -6 divided by -3 is -2. I mean +2. -12 divided by -6 is 2. -24 divided by -12 is also 2. Okay, so we already know our R. Okay. All right, so find A1, R, and AN. So A1, -3, R, we already checked that. And we said it's 2. Okay. So then our AN, so our sequence function is going to be, we're going to be using this, A1, R to the N minus 1. Okay. So plugging in for A1, I get -3. Okay. And plugging in for R, that would be 2 to the N minus 1. Okay, so make sure you leave it like that. This does not simplify to -6 raised to the N minus 1. Okay, and this right here, only 2 is the base with this exponent, not -3 times 2. So just leave it like this. Do not multiply these two together. Okay. All right, so here are our answers. This one right here and here too. Okay. Okay. Let's have a look at this one. Okay, so let's find A1, R, and the AN function for the geometric. For when it says it's geometric, you don't actually have to check it. Just go ahead and find the R. For the geometric sequence 1, square root 3, 3, 3 square root 3. Okay. All right, so we know A1 is 1. We know R is going to be square root 3 divided by 1, which is square root 3. Okay, so once we know those two things, then we can write our AN formula using this. Again, different textbooks use A1 synonymously. Okay, so Okay, so an is going to equal 1 times r, which is square root 3, to the n minus 1. Okay, so different ways to write this. You could, anything times 1 is itself, so you could just write this as square root 3 to the n minus 1. You could also rewrite this so that the radical is written as a fraction exponent, right? So we get this, okay, because that 1/2 exponent means square root, okay? And then you could multiply these exponents together. So another way to write this is n minus 1 over 2, okay? So I'm not sure which one WebAssign will take. So just be aware of this when you have the square root. Just be aware that you could write it as 1/2 and then multiply. Okay. Okay. Let's take a look at another example. Let's find the 8th term of the geometric sequence 5, 15, 45. Okay. So here we see that A1 is 5. We see that R is 15 divided by 5, which is 3. So we see that AN is 5 times 3 to the n minus 1. So if I want the 8th term, A8, then I will plug in 8 into this sequence function and work this out. So that's 3 to the 7th. And punching that into your calculator, you should get 10,935. Okay. Okay, let's do this one. So in a geometric sequence, A3 equals 63 over 4. A6 equals 1,701 over 32. Find A5. Okay, so different ways to do this. You could use systems of equations just like with arithmetic sequences. There's an arithmetic sequence version of this type of problem. And I showed you a different way where you kind of just look at how many times you added D. So here, instead of adding D, you're multiplying by R. So let's just take a look. So A3, A4, A5, A6. Okay, right? And it goes on. We know that A3 is 63 over 4. We know A6 is 1,701 over 32. And we know that we multiplied by R to get to the next term, to get to A4. And then we multiplied by R to get to there. And then we multiplied by R to get to there, right? So we essentially did 63 over 4 times R to the third power, right? And that should give us A6. Okay. So if we solve for R here, okay, I'm going to go ahead and multiply by 4 over 63 on both sides to cancel these. Okay. And here, if you have a calculator, great. If not, let's just do this by hand. That goes 4. 4 goes there once. 4 goes here 8. Okay, and then here 63. Here, this is divisible by 9, and I know that because if I add up the digits, 1 plus 7 plus 0 plus 1, I get 9. And if it's divisible by 9, the sum of these digits is divisible by 9, then this actual number is divisible by 9. Okay, so both of these are divisible by 9. 9 times 7. And that would be 9 times 189. Okay. And then this is actually divisible by 7. 7 will cancel out here. 7 goes into 189 27 times. Okay, so let's write this out on a new line where we have room. Okay, so I get r cubed is equal to 27 over 8 once I did all my cancellations. All right, and this is nice. Take the cube root of both sides, and I get r is equal to the cube root of 27 over 8. Cube root of 27 is 3. Cube root of 8 is 2. Okay, so r equals 3 halves. Okay, and but we need to find a5. And if we look here, right, to get to a5, I just need to do 63 over 4 times r, right? So let's do that. a5 equals 63 over 4 times r squared. We know what r is because we just found it over here. Okay, so times 3 halves squared, 63 over 4 times 9 over 4, and that comes out to be, what does that come out to be? 567 over 16. Okay, so this is just one way to do it. Okay, there's the other way of using systems of equations. Okay, but I feel like this is, I don't know, makes more sense. And it's a little quicker. Okay, let's see. Sums. Let's talk about the sum of a geometric sequence. So what we have here is we can actually take the sum of a finite geometric sequence. So we can take the sum of n number of terms, right? If we take 100 terms, we can find the sum of them, right? We can also, here with geometric sequences, we can also find the sum of infinite terms of a geometric sequence. Okay, so we're going to look at both of those. So let's start with the finite, and then we'll look at the infinite. All right, so sum of a finite geometric sequence. Okay, so if you have a geometric sequence, then and you want to find the sum of the first 100 terms, then that would be your n. Okay, the sum of however many terms, and it is going to equal a1 times 1 minus r to the n all over 1 minus r. Okay, and here your common ratio cannot be 1 because then we get undefined. Okay, so this is a formula you'll need to know for the test. This can also be written using the sigma notation. So it might look like this as well. So maybe you're taking some of the first 50 terms. I won't put 50, I'll just leave this general. Okay, 1 to n terms. Okay, and then you'll have over here, you'll have your geometric sequence function. So you'll have that a1 r to the n minus 1. Okay, that looks like an r. Let me take that off. Okay, so a1 to the r, a1 times r to the n minus 1. Okay. So if you see that, so if you see it written like this, you can still use that formula. Okay, they might spell it out. They might say, they might give you something, something like this, right? And they say, oh, okay, or something like this. And they'll say, oh, find the sum of the first 100 terms. Okay, so you'll still need your AN formula. So you'll need to come up with that. Okay, if you're going to write it in summation form. Okay, but to find the actual sum, you only need A1 and R. And however many terms, the sum of the first 50 terms, plug in 50 for N. Okay, the sum of the first 100 terms, then plug in 100 for R. Okay. All right, so let's take a look here. Find the sum Sn of the first n terms of the geometric sequence 6, 2, 2/3, 2/9. Okay, and we're going to do this for n equals 10. Okay, so in other words, the sum of the first 10 terms. Okay, all right, so so we're going to be using this formula here. Let's go back up. We're going to be using that. Okay, so the sum of the first 10 terms is going to equal A1. Let me bring this down a little. A1, so that's 6 times 1 minus R. R, it's 2 divided by 6. So again, order matters. So you're doing 2 over 6. So R equals 2 over 6, which is 1 over 3. Okay, so 1 over 3 to the 10th power all over 1 minus 1/3. Okay. All right. And then once you punch that all into your calculator, you should get 59,048 over 6,561. Okay. So this is the formula you'll be using. So again, if you need to find the sum of the first 10 terms, 50 terms, whatever it is, you'll be using this one. If it says find the sum of the infinite, not finite, infinite geometric sequence, then you'll be using this next formula, which I'm going to give you. Okay. Infinite geometric series. So the formula for this one, that's a little infinity symbol here. Okay, so the sum for the infinite geometric is going to be A, or A1. That looks like a 9. Hold on. Okay, there we go. So A1 over 1 minus R. Okay. And again, A1, same thing. Okay, so here, if it's written in sigma notation, so this formula is much easier to use. There are no exponents compared to this one over here. You'd have to work that all out. Okay, 3 to the 10th power. Okay, so over here, much simpler formula. And if you see it in sigma notation, then you would be, it's an infinite uh, sequence. So you won't be ending at some number like here. You won't have 50 for finite. That's finite. Okay, the first 50 terms. Okay, so what you're going to see is maybe you'll see, okay, you start from the first term and you'll go all the way to the infinite term, right? Whatever that means, right? Okay, so that's what you would see when they're asking you to find the sum of an infinite geometric series. And over here, you'll still have your sequence function, A1. Here, let me go ahead and write that, A1 or A R to the K minus 1. Okay. Now here's the thing though about this. So this is true if the absolute value of R is less than 1. Okay, so if your absolute value of R is greater than or equal to 1, then we say that the series diverges. Okay, and you wouldn't be able to use this. Okay, so that is pretty much it. Just a lot of formulas in this chapter, and we're going to be getting some more in the next one. Okay, in the next section. Okay, hope you're having an easy time with the homework or keeping up. Okay, so if you have any questions, just email me or message me and I'll get back to you.